Okay, continuing it on. Let me get a share screen going. So all of this was satisfactory, but since doing these two initial attempts, I completed that fabric tutorial with the forward and backward reaching inverse kinematics, which you might remember, and thought it would be fun to have an inverse kinetic controlled arm composed of several joints and links. And let me just show you what this looks like and come in and explain. Here's my crane test uh, that now has uh, an arm that I can maneuver around, and it keeps track of the position of the uh, arm tip, and I can raise and lower it, and I can move it in and out, and all that's pretty cool. This did require a slight modification to the, I've required a few modifications to the script that builds the robot arm, the, like the fabric script. And the main work here ended up being how we would control the arm tip, whose position the IK-controlled arm seeks to attain. We've got a little object out there that we're moving around, and the arm tip is trying to touch it. One approach was to use the mouse buttons 0 and 1 to push the arm tip forward and backward. Just move it forward and backward in horizontal space, and then use the mouse scroll to raise and lower it. But having it kind of move in and out and up and down was not real intuitive. And it also suffered from difficulties when you move the arm tip too far away for the arm to reach. And also, I didn't want the arm tip to move behind the base, and preventing that, the geometry was just turning into a nightmare. So an easier approach was to use a kind of polar coordinate system where I have a distance from the base and I have an angle. And these are easy to clamp. You can clamp your distance is less than the chain's complete length. And you can also limit it from getting too close to the base. And the angle can be greater than 0 and less than some maximum value. Nominally, I set the minimum distance at 5 meters and the maximum angle at 75. This required a slight modification of the fabric script, which was to make the chain's complete length accessible as an exposed public variable. So I wrote a function that gets distance and angle from the arm tip's position. This I only actually called once at the beginning. The arm tip is out there someplace in space, and it has to find it and know what distance and angle to set. So this was a little trick here. I get the vector between the arm tip's position and the transform position. That's the object, that's the crane's root object that the script is on. I get the distance then from just its magnitude. I kind of project this down onto the XZ plane by just taking the X and Z components of it. And I do this as a vector too, so later I can take its magnitude. And the Y component of this original vector is the rise, and the sept vector XZ is the run, and so I can do an inverse tangent rise over run to get the angle that I need. As I said, I only call this once. The one that's more important is the function to set the position of the arm tip given that distance and angle. So now that I have the distance and angle, It's simply sine and cosine to give me the rise and run. Um, um, I'm going to make this into an offset, so it's run times the unit vector in my transform's forward direction. So that gives me a vector run length in the horizontal in the XZ plane. And then I just replace the Y value with the rise, and that puts me up at the position that I want. This vector has changed length, of course, when I added the rise to it. So I'm going to normalize it, scale it by distance, and I position my arm tip at the transform position plus that offset. The function to move the arm tip using the mouse buttons for in and out. I've got a Boolean that the arm moved is false. If I'm pressing the left mouse button, I increment the distance, clamping it to 5 to the complete length minus some little bit, and set arm move to true. If I press the right mouse button, I decrease distance, again clamping it and setting arm movement to true. And if I want to change the angle, I get the mouse scroll delta.y. It's a vector 2, but it ignores the x for the scroll. I guess if you had a trackball mouse, it might pick up an x component as well. If the scroll delta is not 0, then I increment the angle, clamp it to the 0 to 75, set arm move to true. And if arm was moved, I call that set distance angle function that I did up above that just does the sines and cosines. There was that funny bailout at the beginning, a bailout if not ready. And this was necessary because the arm builder, as I wrote it, used coroutines so that it was built basically frame by frame with weights in between the instantiation of each joint and the counting up of the length and some other stuff was all done with coroutines. And so I found that if I started to manipulate the arm before it was completed, things were weird. Also, I wouldn't know the complete length until the arm was completely formed. And this necessitated the second modification of the fabric script, an exposed variable completed creation that is set when the chain is fully formed and ready to go. The arm building was originally in the start function, and I thought maybe just putting it in the awake function would allow me to simply do fast IK as transform get component in children and find my fabric script, after which I could then access whether it had been completed and get the complete length, both of those exposed public variables. Unfortunately, this wasn't the case. I had to get fancier. And my solution to this was to make the start a coroutine that then yields another coroutine. And you remember a yield in a coroutine blocks on that until it returns. And so this is going to block here until find fast IK is done. And find fast IK, the coroutine is going to do a few loops testing to see if the fabric script exists. At first, it doesn't exist because it's actually added to the last link of the arm. So this is why I couldn't find it to begin with. And so this, and it waits for a little while in between each turn of the loop here, asking to find it. If it does find it, and if it's completed, then ask for the completed length. And all of this was necessary to get the full deal when the arm is being built with a coroutine based function. Um, I had thought of putting a yield break in after getting the completed length, but I found that even this didn't work. It often came up with the wrong length of the arm. I have no idea why, but it did. So ultimately, it has to do uh, uh, five turns of the loop, 5 seconds worth of work. It does get it in that amount of time. One other detail that I had to deal with was damaging the arm when it's hit by a falling block. That was easy with the single object arm. That was just a single beam, but it was more difficult with one made of several objects. I'll let you read that script yourself. Um, One other thing that was kind of puzzling was that the default physics, with the default physics settings, the chain of the fabric arm, uh, which turns out to be much more maneuverable than the rigid beam arm, could get the wrecking ball swinging much faster. And this made the chain kind of visually fall apart. It just stretched and the pieces all got jagged. And the fix turned out to be a physics setting for the solver type, which by default is projected Gauss-Seidel. And I found that changing this to temporal Gauss-Seidel made the chain much more stable. In the documentation, it says the solver offers better convergence and a better handling of high mass ratios, minimizes energy introduced when correcting penetrations, and improves the resistance of joints to overstretch, which was exactly the problem I was having. It helps when you experience erratic behavior, which I was. So that fixed that problem. And in the process of doing this, I also found that you can override the default iteration count for individual rigid bodies. If you remember, the iteration count is a physics setting with a default value of 6. And they say that larger makes for more accurate, but of course, more expensive physics. I didn't find that this fixed my problems even when I did increase it, but it's nice to know that you can. So let's look now at the fast IK. The fast IK with 1 kilogram blocks. And I've got my little, you noticed I had it said patient please. Let me restart that so that you can see it. It's not ready, patience please. That's because it hasn't yet completed the construction of the arm and everything. So with my mouse, I can push this thing out and pull it back in. I can change my angle with the scroll wheel, and I can start swinging this thing and get the thing going here. And I can knock down the tower. So everything's working exactly as I wanted it to. So all very cool. So I'm going to stop sharing at that point, and I'm going to stop the recording. So I'll see you all in class. Bye. I had fun with this one.